phones on. Can you please turn them off because I can't do anything about the interference with mobile phones.
All right. Next elevator pitch will be given by Samuel, and he will talk about an algorithm for the free energy of one-dimensional quantum systems.
Thank you. So thanks for the introduction. As already mentioned, I'm going to talk about one-dimensional quantum systems. It's a bit of a bulky title, but I think it has partly been already motivated by earlier talks today. This is joint work with Hamza and Omar Fauzi. The setting we are working in is a one-dimensional quantum system. So think of some like atoms, some atoms with like, for example, just a spin degree of freedom on every side. This will always be modeled by like, for example, here, two-dimensional Hilbert space. And we want to ask something about this system and its thermal equilibrium. So we put it at some temperature, like in an actual experiment, and then we want some physical observables out of the system. It's a bit similar to what Joel told us earlier. We also have some very simple description of the interactions in the system, so just like interactions between neighboring particles. Think of like ferromagnetic interactions which align spins and give an energy penalty to non-aligned spins as here. And the only thing that comes into the description of our problem is basically just this small matrix H here, which is just a d squared matrix, so not particularly big. But on the other hand, a system of many particles is then described by a d to the n times d to the n matrix. So as soon as you take many particles, you can basically not even write this matrix down. Not to mention solving the problem that we're interested in, which is we're looking at the free energy of the system. You have also a quite big expression here. Basically, you take this matrix H, which was the sum of these small matrices. So it's a sparse matrix with a like simple description, but the matrix itself is just big. So the exponential of this matrix you can basically not even compute straightforwardly. Then we take the trace and, okay, think of this as some post-processing. We're interested in the limit of a large chain. So as in physical systems, which tend to be quite big, we just take the limit of infinite system size, which makes it even harder to compute this quantity. The free energy itself is actually not a physical quantity. You can't really directly measure it. But it's like a proxy for all interesting physical problems, like, for example, magnetization of your system. You will obtain it as a derivative of the free energy. And also, if you look for phase transitions in materials, which, to be honest, you will not find in 1D, but still, phase transitions are generally marked by non-analyticities of this function f. So it's a proxy for all these things, and it's also in complexity theory quite common to look at this quantity just to cover, in general, how to treat systems in thermal equilibrium. There's maybe also a more physical way of writing down this quantity, because this is a very more combinatorial way of writing it down. You can also regard it as some functional, giving you the energy of the system minus the entropy times the temperature of the system. So it basically minimizes the functional, where you try at large temperatures to make it as unordered as possible, and for low temperatures to reduce the energy. In this case, if you minimize this functional, the minimizer here is basically the thermal state of your system. From this quantity, you can also see if you take the temperature to 0 and you don't regard the entropy at all, then you just minimize the energy. So also this problem of the free energy includes in some limit, if you take beta to infinity, as a ground state energy. So this is basically the problem we're interested in. And in the setting we look at, we propose an algorithm to solve this problem. I just wrote down what's the input and output of this algorithm. Basically, as we look at a translation invariant setting, you don't have that many inputs. You just have this one single matrix describing the interaction. And on top, we also ask for a certain precision that our algorithm has to achieve. Just to make sure, compared to the talks previously, we don't have a quantum computer and we don't use machine learning. This is just a classical algorithm. So it does take this precision that we want to achieve and basically the description of our system and gives us an estimation of the free energy. And what we achieved in our result is basically this runtime. It's basically the only problem input that is interesting. So you want to ask what is the runtime in terms of the precision you want to achieve. And it is exponential in logarithm 1 over epsilon divided by something. So at least slightly better than any polynomial in 1 over epsilon, which is the previously best known algorithm for this problem. I didn't talk about temperature here. It's important to note that this will only work at a fixed temperature. If you actually look at the temperature dependence of the algorithm, it's quite bad. You should expect this, because it's known from complexity theory that's a ground state problem, which I mentioned we could also in principle solve by taking a limit. But the ground state problem is computationally hard. It's not even expected to be solved with a quantum computer. So you should not expect to get a favorable dependency on the temperature in this algorithm. Furthermore, I also mentioned beforehand, you can use this free energy to compute thermal expectation values and things. Actually, our algorithm immediately gives a description of the thermal state as well. So you can just take it as an output from our algorithm. I'm not going to explain in detail how the algorithm works, but I'm going to look at the classical case first. This will give some insight in the method we use, or it will like kind of motivate it, because basically a similar approach, also a bit more tedious in the quantum case, holds as well. Before that, just in case you don't care so much about 1 over log 1 over epsilon improvements, I can also assure you that our algorithm actually works. We implemented it. The implementation is quite simple. It's just a few lines of code. And then you can look, for example, if you're computing the energy. This L is just a parameter in algorithm, basically describes for what time we're running it. But even the L equals 10 case is basically just running for a few seconds. Or here L equals 11 for like 10 seconds. We didn't run it for longer than that. But already we achieve, at least for these low beta parameters, so for high temperatures, error rates going close to like machine precision. So basically don't have to look further if you're getting there. As I said, we don't expect it to work for very high beta. We still get like decent results at beta equals like 10. Still can get a reasonable precision, but further for higher beta at some point it has to fail due to these complexity theoretic barriers. This is just a toy example we use where we have an analytic solution to compare to the Heisenberg XZ model, but that's not too important here, I guess. So as I said, let's just have a look at the classical case. Again, we see this beforehand. We had this trace of e to the minus beta, the whole Hamiltonian. In the classical case, these are just like small matrices telling you what's the interaction energy for any configuration of neighboring particles. So like you will have the energy of 2 up spins or the energy of an up and a down spin and 2 down spins, all in this small matrix H. Unfortunately, in the classical case, this just all commutes. You can just take your exponential apart and write just for all for every bond, write this factor separately. And the sum is also actually only, if you sum over any configurations, the sum over the first side basically just applies to these 2 factors. What you can see here, it looks like a matrix multiplication because it is a matrix multiplication. These factors are the matrices with indices I1, I2. We call this matrix T. And then if you figure this out, this is actually just a big product of n matrices, and you take a trace of it. So something that is actually very simple to compute. You just diagonalize this matrix T, which just is basically immediately given by your problem input. You figure out its eigenvectors and eigenvalues, and then you see this is all the eigenvalues to the power n summed up. Unfortunately, also, because this matrix has only positive entries, there's a Perron-Frobenius theory which actually tells you the dominant eigenvalue of this will exist, it will be real. So this basically always will work. Yeah, this is the thing I'm mentioning. Basically, as soon as you normalize, only the dominant eigenvalue will matter for this problem. So actually, you only solve this problem, find for this matrix T, the eigenvector corresponding to the maximum eigenvalue. Immediately, you have a formula for the free energy. Very simple. Just take this, just a finite dimensional linear algebra problem. And also, if you actually search a description of the thermal state, this will be given more or less just by this eigenvector. It's basically the one-side probability distribution of your system. And then using this transfer matrix, you can also construct the probability distributions on several sites. This all works basically because a classical thermal state with just local interactions as a Markov chain. So whenever you have like 3 regions lined up, and you have a spin in the middle, then everything happening on the right of the spin will only depend on the spin in the middle, not on anything on the left of the spin. For quantum systems, this is not quite true. But just to give you a rough idea of what we are doing, we're kind of transferring this idea to quantum systems and use something which looks a bit more scary than the transfer matrix beforehand. But you can kind of see the same thing again. You have just something like e to the minus beta h1, 2, and if everything would commute, this map basically is like the classical case. So this is the non-commutative analogon of this classical transfer matrix. It will act on more sides. You also see this parameter of your algorithm that I mentioned beforehand. And basically, again, just the spectral radius of this map and the corresponding eigenvector will give you the result we're looking for, the free energy, apart from taking a logarithm. The only thing is that it does not work immediately. It's not just a matrix going from one to the next side, but if you involve several sides, you basically converge to the value you're looking for, just to give you a rough idea of how this works. This is the motivation of like the proof idea, and I think with that I'm already about to conclude, and I'm happy to take any questions.
Any questions? Yeah, I don't have any questions, so no questions, then let's just move on. Let's thank Samuel again one more time for the nice talk.